Hey everyone, welcome to 5.3 Part 2, Inverses, and we're talking about inverses as they are dealt with in calculus. So the first question that we could ask is, do all functions even have an inverse? And how you can actually do that is you can check for if something is even a function by using the vertical line test, right? And then what we're going to do is if you want to check for if something has an inverse, you want to check the horizontal line test because there's the same idea, but it's just going to be a horizontal line to see if that works out. So what we're going to do is let's just get a couple of examples here. And let's look at, well, let's just look at this one first. So we're looking at, first of all, is this, there we go, a vertical line test. So as we go this way, you say, yes, it passes the vertical line test because it only crosses at one point. Okay, good. So that one is a function. But now, oops, hey, whoa, let's go back here. That's better. So now what we're going to do is let's look at, is its inverse going to also be a function? So if I do the horizontal line test, say, okay, I'm going across, and this function only touches this graph once as well, then we can say that function is a function and it has an inverse because it's got both horizontal and vertical line test that it passes. So let's look at this one. Let's look at the vertical line test. Is this a function? Yes, it is. Okay, and then is it a vertical, or is it the inverse? Does it even have an inverse? We'd say right here, no, because we've got this point, we've got this point, we've got this point. These 3 points tell us it's not going to be a function as the inverse. Now the original function is a function, but its inverse is not. So this x cubed minus x plus 1 does not have an inverse. Alright, good. So check for a function, vertical line test, check for an inverse, horizontal line test. And so now let's get to theorem 5.7. The existence of an inverse function. A function has an inverse if and only if it is 1, 2, 1, which means it passes the horizontal and vertical line test. Alright, then that's called 1, 2, 1. So you'll get both vertical and horizontal, and if that happens, then the function has an inverse. Alright, so that's one option. The other option is if f is strictly monotonic on its entire domain, then it is 1 to 1, and therefore it has an inverse. This word monotonic means always increasing or decreasing. So if it's increasing or decreasing, whoa, then we know that it is going to be a function and it has an inverse. So if it's just increasing or decreasing the whole time, you are good. Alright, so let's look at an example. Does this function have an inverse? And these are the ones we actually did, so let's look back. X cubed plus x minus 1. That was our first one right here. Is this one going to pass the horizontal line test? Yes, it does. Alright, so the first one, we can say, yes, it does, just by looking at the graph. Okay, and we say, does the other function have an inverse? Well, let's look at this one. And we say, does it pass the horizontal line test? And we go right here and say, no, we've got a problem because the horizontal line test touches the graph at more than 1 point. So we can say no for that one. All right, so using graphs is a good way to check for inverses. Here are some other guidelines that you can use to help find an inverse. First, you can use that 5.7. Use the horizontal and vertical line test. Is it 1 to 1, or is it always increasing or decreasing? Then you know it's going to be a function. You can solve for x as a function of y, meaning solve for x and then say g of y, and there you go. That's going to be your inverse. You kind of switch the x's and y's and solve for x. That's number 3. Switch the x and the y. Number 4, define the domain of f inverse to be the range of f. So we just have a set of numbers. Switch them with the domain and range. There you go. There is an inverse as well. And then number 5, verify f times, or f of f inverse of x equals x, and then f inverse of f of x equals x as well. So you can just plug some stuff in, and there you go. All right. So now let's do this example right here. So let's just set this y equals the square root of 2x minus 3, and then let's solve for x. So we're going to square both sides first. You can say y squared equals 2x minus 3. And you're going to add 3 and then divide by 2. So I'm going to do that all at one time. Y squared plus 3 all over 2 equals x. Okay, so that would be the inverse after we switch the x and the y. So then all we have to do is say y would then equal x squared plus 3 over 2. And then that would be our inverse of f of x. You'd say f inverse of x equals x squared plus 3 all over 2. Now you could also switch x and y first, but either way you're going to get the exact same answer. All right, good. So the next one says that we're going to show that f of x equals sine x is not one-to-one on the real line, but it is on the interval from negative pi over 2 to pi over 2. Okay, so let's go through here and let's say we want sine x. Let's graph it. We don't want this one anymore, and we don't need this one anymore. So here we go. And we're going to say, is this, first of all, is sine a function? Yes, it is. Never. We don't have more than one y value for each x value. Now, is it a horizontal line test passer? No, which means right here we have an infinite amount of points. If I keep going this way, you're going to say, yep, it keeps on hitting more and more points, so therefore it's going to not pass the horizontal line test. So the whole thing is not a function, right? It doesn't have an inverse. So, but we know that inverse sine is something you've learned in trig. So we know that inverse sine is something, and if you remember from trig, we know that inverse sine is actually defined as from pi over 2 to negative pi over 2. So we're only looking at this region right in here, from between the red and the green. All right. So if I go there and I say, now let's look at the horizontal line test only in this area. Maybe we can even zoom in a little bit more for this. So we're only looking between the red and the green. If I go up and down here, I get once all the way to the top. Right? If I were to go any further out here, then I would have 2 times where it does not cross the y-intercept, or does not cross past the horizontal line test anymore. Right here, if I were to extend this green one out, then I'd have this point and this point. Then we'd say, nope, it's not the inverse does not exist. But if we go only to this point right here, only to pi over 2, then we have the top to the bottom, and we'd say that is a function. So sine, the inverse of sine does exist on the domain of pi over 2 negative to pi over 2. All right, so it is restricted on that area because otherwise it would not be a function. Okay, good. So let's go on to theorem 5.8. There's a whole bunch of stuff. Continuity and differentiability. All right, let f be a function whose domain is an interval I. So it has to be some interval. It could be infinity to infinity, but it has to be some interval. If f has an inverse, then we can say these things. 1, if f is continuous on its domain, then the inverse is continuous on its domain. If f is increasing on its domain, then inverse of f is increasing on its domain. If f is decreasing on its domain, then inverse of f is decreasing on its domain. If f is differentiable at c, and f prime of c does not equal 0, then the inverse of f is differentiable at f of c. So all that stuff happens. Great. Now here's theorem 5.9. The derivative of an inverse. Let f be a function that is differentiable on an interval I. If f has an inverse function g, then g is differentiable on any x for which f prime of g of x does not equal 0. And then we can also say g prime equals 1 over f prime of g of x, where f prime of g of x does not equal 0. All right, so you say, great, how is that really all that helpful? Well, we're going to do an example with that one right here, right now. So here's your example. Let f of x equal 1/4 x cubed plus x minus 1. What's the value of f inverse of x when x equals 3? So that's the first question. What is that thing going to equal when x equals 3? So really what we want to find is f inverse of 3 equals what? Okay, which is another way of saying, remember that the x and the y's are just going to switch. I can say that's the same as f of x equals 3. What does x equal? All right, so what I'm going to do is let's go back here to my graph, and I'm going to get rid of some of this stuff. And let's look at my new graph right here. So here is my original f of x, okay? And what I want to know is, when does this equal 3? I'm going to zoom out just a little bit. When does this equal 3? Well, oh, it's right there. Right, so I'm not going to say exactly because I can't quite get there. Oh, I had it right there at the end. So when does f of x equal 3? Well, that's when x equals 2. Okay, so that means f prime of 3, just all we have to do is switch those two things, because that's what an inverse is, switch the x and the y, right? So that means f prime, or f inverse of 3 equals 2. So that would be my answer. F inverse of 3 equals 2. So that's the value. And the question is, what is the value of the inverse prime of x when x equals 3? Okay, so remember, f inverse prime of x is going to equal 1 over f of f prime, or f inverse of x. Just like that. Okay, so what we're going to do is we're going to try and plug some stuff in. So we can say this whole thing is going to equal 1 over f prime, sorry, it should be f prime right there, right? F prime of the inverse, f inverse of 3. And it's 1 over all that. And we know that's going to be the same as 1 over f of, do we know what the inverse of f at 3 is? Yes, we do. We know that's actually 2. So we can say that's really f of 2, f prime of 2. So that whole thing is going to be f prime of 2. So now we say, well, if we know what that f of x equals 1/4 x cubed plus x minus 1, f prime of x is going to equal, bring that 3 out in front, 3/4 x squared plus 1. Right? Okay, so that means we can just go in here and say this is going to be the same as 1 over, we're going to say 3/4 of 2 squared plus 1. Where did I get that 2 from? Well, right here. I'm using the 2, and I'm plugging into all the x's that I see in there, right? So that's where that 2 came from. And we just have this 1 over that. So that's going to be the same as 1 over 4 times 3/4 is going to be just 3 plus 1 is going to equal 1/4. So we can say that f prime, f inverse prime of x at x equals 3 is going to be 1/4. Now what's really interesting about that is that f prime of x is going to equal 4. So really, it's kind of the same thing as being able to plug in some reciprocals. And we can actually say that dy over dx equals 1 over dx over dy. So we can kind of use some of that. Now do you have to, or can you just plug some stuff in? Absolutely. Just plug some stuff in and you got it. All right, so there you go. I won't talk anymore. Good luck with the rest of the assignment.